We've talked about maximums and minimums. Today we're going to put those to use in optimization problems, finding maximums and minimums that we would like to optimize. Maximize your profits, minimize your expenses, things like that. Have real applications. So our steps in optimization problems is it often helps to draw and label a diagram and write an equation involving the quantity to be maximized or minimized. So if you want a maximum area, better have an area equation. You want maximum profit, better have a profit equation. Minimum distance, you want a distance equation. Now, there's some relationships given to you in the problem that may help you reduce the number of variables, and so we should look for that. And then we're going to have an equation that we would like to use derivatives, because derivatives help us find maximums or minimums. So those are going to be the 4 steps that we use. We'll start out with an easy example, and then we'll jump to a pretty tough one. But a dog owner wants to bury a wire in the ground, makes an invisible fence, keeps his dog in the yard, and he's got 1,000 feet of wire. So, what are the dimensions of this rectangular region that will give him the largest possible area? So we'll draw a picture of a rectangle. There, we're going to draw a rectangle. There we go. And the area has a length times a width. And it's got another length and it's got another width. And let's see, we want largest possible area. So the area of this rectangle is length times width. Now we want to reduce the number of variables. So what do we know? Well, we know there's been a relationship given to us in this problem. And that is that the perimeter of this thing, 1,000 feet of wire, that is 2 of these L's plus 2 of these W's. So I'm going to solve for one of those variables so I can get rid of that variable. Let's solve for L. 1,000 minus 2 W's is what 2L is equal to. When we divide each side by 2, we get 500 minus W is equal to L. So I'm going to get rid of these L's. And I'm going to replace my L's. 500 minus W. So now my area equation has fewer variables. Instead of an L, I'm going to say 500W, 500 minus W, times W. And so the area of this thing is 500W minus W squared. Now, let's go back and look at our steps. We drew a diagram. We wrote an equation involving the quantity to be maximized or minimized using the variables in the diagram. We did reduce the number of variables using the relationship that was given. And now we're going to find the derivative. And so the derivative, A primed, is equal to, and we're using the variable W here. W is our variable. So A prime using the variable W is, well, let's see, if W is our variable, the derivative is going to be 500 minus 2W. And I want the derivative to equal 0. So 500 is going to equal 2W. When the derivative is 0, we've got our critical number, which is why we did that. So W is going to have to be 250. Now, that's the only critical number I get, is that W is 250. So I'm assuming that that is my minimum. Now, if I were to actually make a sign chart and put a 250 on here, I know if I choose anything less than 250, I get a positive value for my derivative. If I choose anything greater than 250, I get a negative value for my derivative. And so yes, at 250, we are going to have a maximum value for our area. So the dimensions of this region are W, which is 250, by L. L is 500 minus W. So we are going to have a rectangle that is actually a square. Now these are tough. These are tough, these are time consuming. May have to press pause to process a little bit here. We've got a parabola, y squared equals 2x. And since it's a y squared equaling 2x, this is a side opening parabola. This side opening parabola opens something like this. Now I would like the point on that red parabola that is closest to the point 1, 4. So there's 1, 4. I'll label that. And there's some point on the parabola here where that is the smallest possible distance. I don't know what that point is. I'll call it xy. And the value I'd like to maximize or minimize, in this case minimize, is distance. So I have to use the distance formula. And distance formula is equal to the square root. Well, now wait a second. I know I'm going to have to take the derivative of this thing. So instead of saying square root, I'm going to say that it's something to the 1/2 power. Now, distance formula is the square root of, I'm going to take x2 minus x1 squared plus y2 minus y1 squared. And that's the distance, and that's what I'd like to minimize. Now, do I have a relationship that helps me get rid of some of these variables, or one of these variables? And this is the relationship I've been given. What is it easiest to solve for, x or y? And that opinion may vary. But I think if y squared equals 2x, then it's pretty easy to say x is equal to y squared over 2. So I'm going to write my distance formula as y squared over 2 minus 1 squared plus y minus 4 squared, all to the 1/2 power. And I have just written this distance formula, and I should probably write this ever so slightly differently. This is the distance using the variable y. So I've got my drawing, I've got my equation, I've reduced my variables. So now it's derivative time. And let's set the derivative equal to 0. Let's see, I would have to do a chain rule, 1/2. Don't mess with what's inside. And that's going to be to the negative 1/2. So all that's going down to the bottom along with this 2 times the derivative of what's inside. And I'll have to chain rule this. I'll have to take 2 y squared over 2 minus 1 to the first power times the derivative of what's inside, and the derivative of y squared over 2 is just going to be y. Plus, I've got to take the derivative of this, so I've got 2 chain rule. I've got to bring my 2 around front. Don't mess with what's inside. To the first power times the derivative of what's inside, which is 1. So, I want this derivative to be equal to 0. Now, anytime a fraction is equal to 0, it's because the top is equal to 0. Remember, this part right here, along with this 2, all went down to the bottom. This went to the bottom because of the negative exponent. So the numerator is this stuff right here. Really, I'm going to focus my attention on this stuff right here being equal to 0. So if I were to multiply this out, I have y squared times this y, or y cubed, minus 2 times y, plus 2y minus 8 is equal to 0. Well, that's pretty nice. Those cancel out, and y cubed minus 8 equals 0. Y cubed will equal 8. So y will equal 2. And so I want to find the point. I need an x and y value, and I know the y value is 2. And if I'm looking for the x value, I'm probably coming right here. I'm putting my y value of 2 in there. And 2 squared is 4. 4 divided by 2 is? xy is the point 2, 2. That is the point on the parabola closest to 1, 4. This right here looked really ugly. But keep in mind, you want that derivative to be equal to 0. You want to find your critical value. Just focus your attention on the numerator. Now, a box with an open top and a base that has length twice the width is made from 1,600 square centimeters cardboard. What's the largest possible volume? Well, let's draw a box like that. All right. call this the width. Let's call this the length. Let's call this the height. And what we'd like to maximize is the volume. And that's length times width times height. Well, now we got to whittle down our number of variables here. I do know that the length is twice the width. So instead of an L, what if I called that 2 W's? So instead of this L, let's call it 2W. That's better. Still might be too many variables, but there's another relationship that's given to us in this problem. We were actually given a couple of them. The other relationship is that we've got 1,600 square centimeters, and that's an area. So let's focus our attention on the area of this box, this 1,600. Now, that includes the area of the bottom of the box, which is 2W squared, as I take the length of that times the width of that. And then we've got four sides. We've got this side right here, which is 2WH, which is the same as this side over here. And then we've got this front side of the box, which is WH, and so is the back of the box. So we've got a WH plus a WH. So 1,600 equals 2W squared. And if I add all of these like terms together, I'm going to get 6 WHs. Now, what variable is it easiest to solve for? I think we'd agree that the easiest variable to solve for is h. So 1,600 minus 2W squared equals 6WH. If we divide by 6W, we have solved for h. 1,600 minus 2W squared over 6W. Well, then our volume, in terms of the variable W, can be written as 2W squared times this 1,600 minus 2W squared over 6W. And the volume is all in terms of W. Now, before I take the derivative, let's see what we can do to simplify. I think this 2 and this 6 would give us a 3 down on the bottom. I think that when we have a W squared on top and a W on the bottom, that one of those W's cancels out, factors out. And so I think the volume in terms of W can be written as, let's see, 1,600 W divided by this 3 on the bottom minus 2W cubed over this 3 that's on the bottom. I think that'll be fine. Because now that looks like something that taking the derivative wouldn't be all that bad. The derivative in terms of W. Derivative of this guy, 1600 over 3. Minus, well, let's see now. Let's bring that 3 around front. And I think we're going to get 2W squared. And we'd like to find the value of W that makes that 0, that critical value. And I think we might find 2 of them. But one's going to be positive and one's going to be negative, and the negative one can't possibly be. So let's say 1600 over 3 equals 2W squared. So 1600 divided by 6 equals W squared. Now what they want is they would like the largest possible volume. So your job now is to figure out what does W have to equal. And once you've found that, can you use this equation right here? Now that you know what W equals, what that critical value of W is, can you use this to find that maximum volume of your box? So take a moment with your calculator, press pause, and let's see what you come up with, see what I come up with. These are the numbers that I came up with for W and for V. Now, this last digit would have been a 7 if I truncated, 8 if I rounded. Remember, when you are finding the volume, you've got to use all your digits for W so that you can get volume correct to 3 decimal places. So that's how we're going to use derivatives to find the optimization, the optimal values that we need to maximize or minimize quantities.